All right, so today we're going to dive deep, really deep, into some of the inner workings of Amazon Athena.
Sounds good.
Specifically, obviously Amazon Athena is this incredibly useful serverless,
Yeah.
lets you query, data in S3, all sorts of different formats like CSV and JSON.
Mm-hmm.
And but today we're going to be looking at some of the optimizations that they've been doing under the hood.
Right.
So to get started, I think it might be useful just for the listeners who maybe haven't used Athena before or are not super familiar.
Sure.
Maybe we could just kind of quickly level set on what exactly Athena is.
Sure. So Athena is a service from AWS, and it's fully serverless. You don't have to worry about any servers.
Yeah.
And it lets you query data that's stored in S3 in open formats such as like CSV, JSON, ORC, Avro, Parquet.
Right.
And you can query that data using standard SQL, and you don't have to do any ETL. So you can just point Athena at your S3 bucket.
Yeah.
And start querying your data.
And these can be really huge, right? I mean, that's kind of the point. That's right.
Yeah, I mean, we're talking about truly big data kind of stuff.
Yeah.
And it can even handle, compressed files.
Right.
Like if you've got things zipped up with like Snappy or JuZip or something like that.
Correct. That's right.
So it really kind of lives up to that promise of, serverless and really kind of just handles all of the infrastructure and everything for you.
That's right. You don't need to know anything about the underlying infrastructure.
Yeah.
It just works.
Right.
And it scales automatically
Yep.
based on the size of your data and the complexity of your queries.
Right. And of course, you only pay for the data that you scan when you run your query.
That's right. It's the pay-as-you-go model.
Yeah.
So you only pay for what you use.
So I think that's a pretty good level set for folks who maybe weren't super familiar.
Yeah.
And I think it's interesting because, Athena is built on, has its roots in this project called Presto.
Right. And so maybe you can talk a little bit about that because, Athena isn't Presto, but it kind of was inspired by and has sort of taken some of the...
Yeah, so Athena's query engine is actually based on Presto.
Okay.
And Presto is an open source distributed SQL query engine.
Okay.
That was originally developed at Facebook.
Okay.
And so Athena uses a lot of the same design principles as Presto,
Mm-hmm.
including the idea of streaming data during query compilation, scheduling, and execution.
Right, right. And that's one of the things that we're going to be talking about today, which is this idea of streaming.
Yeah.
And so maybe we could start there. Like, what does it mean when we say that Athena streams data?
So streaming means that Athena can start processing your data and returning results as it's reading the data.
Okay.
So it doesn't have to read all of the data into memory before it can start processing it.
Right.
Which can make queries run much faster.
Right, especially when you're talking about like truly huge data sets.
Especially for large data sets. Yeah.
Yeah, you don't have to, read in a terabyte of data and then start working on it.
Okay.
You can actually start processing as it's streaming in.
Yeah, that's right.
So the kind of the focus of our deep dive today is on this paper, which talks about some interesting situations where that streaming approach can actually lead to, some suboptimal executions.
Right.
So maybe we could start talking about, what are those situations where streaming might not be the most efficient thing?
Yeah, so one of the situations where streaming can be suboptimal is when you have common sub-expressions in your queries.
Right.
So common sub-expressions are essentially just parts of your query that are repeated.
Mm-hmm, yeah.
And because Athena is streaming the data,
Right.
it might end up evaluating these common sub-expressions multiple times.
Right. So you're kind of doing the same work over and over again.
That's right.
And obviously that's not the most efficient thing in the world.
Right. It can lead to longer query runtimes and also increased cost.
Right. Because you're paying for the data scanned.
Exactly.
So the more times you scan the same data, the more you're paying.
That's right.
So, fortunately, the folks at AWS who work on Athena are very smart people, and they thought about this problem.
Yeah.
And so the paper we're looking at is about, some new optimization that they've implemented to address this particular issue.
Yeah, so they've implemented a number of new optimizations in Athena that are designed to handle these common sub-expression scenarios.
Right.
And the key idea is to try to eliminate the duplicated work without having to materialize intermediate results or resort to traditional approaches like spooling.
Right. So like the traditional way of handling this might be to, calculate that common sub-expression once and then,
Right.
store it somewhere temporarily.
Store it somewhere. Yeah.
But obviously that that comes with its own overhead.
Right. It adds overhead,
Yeah.
and it can also, be complex to manage. So
Yeah.
these new optimizations are designed to try to avoid that overhead.
Right. And still eliminate the duplicated work.
Right. And kind of the key idea is to, maintain these streaming characteristics of the engine.
Right.
So you're not giving up on streaming. You're just finding smarter ways to
handle it, yeah.
handle those common sub-expressions.
That's right.
So to really kind of make this concrete, I know in the paper they have this example based on, this pretty well-known industry benchmark called TPCDS.
Mm-hmm.
And so I guess maybe we could walk through that example because I think it really illustrates what they're doing here.
Sure. So the example that they give in the paper is based on TPCDS query 65.
Right.
And this query has a common sub-expression in the where clause.
Right.
So essentially the subquery is being evaluated twice.
Right.
And in the optimized version of the query, they rewrite it using a window function.
Okay.
And so window functions are a way to perform calculations across a set of rows that are related to the current row.
And so by using a window function, they're able to eliminate the need to evaluate the subquery twice.
Right.
And instead they just evaluate it once.
Okay, so you're basically calculating this intermediate result once.
Right.
And then using the window function to kind of slice and dice it.
That's right.
As needed.
Exactly.
And I guess, obviously this is all kind of happening behind the scenes.
Right.
But just to give folks a sense of what the query actually looks like. The original query has this part in the where clause that says, sales.ss.customer.sesc equals customer.c.customer.scag.
Right.
And then, a bunch of other conditions.
Right.
And then it repeats that same join condition, sales.ss.customer.sex equals customer.c.customer.seg. And so that's the common sub-expression.
Right. That's the common sub.
That's being evaluated twice.
Yeah.
And so in the rewritten version, using this window function, you essentially have this window function that's calculating, I think in this case, it's the average revenue per store.
Right.
And so it's able to get all the information that it needs from that one calculation. And it doesn't have to do that join twice.
Exactly.
And the results, are pretty impressive, right?
Yeah, the results are very impressive.
Yeah. Was it like a 48% reduction in query latency?
That's right. 48% reduction in query latency.
Yeah. So almost, cutting the query runtime in half.
Yeah.
And then I think also pretty significant reduction in data scanned.
Yes. Almost 50% reduction in data scanned.
Which, of course, translates to cost savings.
Exactly.
So, this is great for folks who are running these kinds of queries. But I think it's also interesting to think about, what are some of the other situations where, these optimizations can be applied.
Right.
Because, not every query is going to have that exact same sub-expression repeated verbatim.
That's right. Yeah.
So, what about cases where the expressions are similar but not identical?
Yeah. So they also talk about that in the paper. They talk about how they can handle near common expressions.
Right.
So these are expressions that are almost the same.
Right.
But they might have slight differences.
Right. Right.
Like, for example, you might have two subqueries that are filtering on different values, but otherwise they're very similar.
Yeah, yeah.
And so the approach that they take here is to rewrite the queries to generate a superset of the data that both subqueries need.
Okay.
And then they apply what they call compensating actions to get the specific results that are required by each subquery.
Right. So you're kind of doing a little bit more work up front.
Right.
But then you're avoiding that repeated work.
That's right.
Yeah.
So they give an example of this in the paper where they have a query that's using a union all operation. And so the query is something like, with country A and then some subquery, select customer ID from sick data, where first name equals John. Union all select customer ID from sick data, where last name equals Smith.
Right. So each branch of the union is looking at that same common table expression.
Right.
But it's filtering on a different column.
Exactly.
Right.
And so the rewritten version of this query, they essentially join the CTE with a small artificial set of values.
Okay.
And then they use the where clause to filter on both the first name and the last name.
Right, right.
So they're essentially evaluating the CTE once and then using the where clause to get the specific results that they need.
Right. So it's kind of a clever way of, you're basically tricking the engine into
Right.
evaluating that once.
That's right.
And then using some of the mechanisms to kind of get the results that you want.
Exactly.
Yeah.
So it's a very clever optimization.
So when you look at the kind of the overall results of implementing all these different optimizations, what was kind of the impact on the TPCDS benchmark?
So on the TPCDS benchmark, they saw an overall performance improvement of over 14%.
Okay, wow.
And for the queries that were applicable for these techniques, the improvement was almost 60%.
Wow, that's incredible.
Yeah, it's a huge improvement.
Yeah.
And I think what's really interesting about this work is that it's not just applicable to Athena.
Right.
These techniques are actually applicable to any query rewriting-based database system.
Right. So this is really kind of pushing forward the state of the art.
Exactly.
In terms of how we optimize queries.
Yeah, and in fact, they mentioned in the paper that these techniques are already being incorporated into other AWS data analytics services.
Right, like Redshift and EMR.
Like Redshift and EMR, yeah.
Yeah.
So it's not just limited to Athena.
So I think we've talked about the high level, what are these optimizations? What's the impacts? But I think it might be interesting to kind of dive a little bit deeper into some of the technical details.
Sure.
Of how they're actually doing this.
Yeah.
I know in the paper they talk about, this idea of query fusion primitives. And then they have these optimization rules that are built on top of those primitives.
Right.
So maybe we could start with, what are these query fusion primitives?
Yeah, so query fusion is essentially the process of taking two or more subqueries and merging them into a single, more efficient query.
Okay.
And the way that they do this in Athena is they define a set of query fusion primitives, which are essentially functions that can be used to merge different types of query operations.
Right.
So, for example, they have primitives for merging table scans, merging filters, merging projections, merging joins, merging aggregations.
Okay.
And so these primitives are essentially the building blocks that they use to define their optimization rules.
Right. So it's kind of like, if you think about, building a house, you have these basic building materials, like bricks and wood and so on.
Yeah.
And then you use those to construct, the walls and the roof and everything.
Exactly.
So in this case, the query fusion primitives are kind of like those basic building materials.
That's right.
And then the optimization rules are kind of like the blueprints for how to put it all together.
Exactly.
Yeah.
That's a good analogy.
So maybe we could talk a little bit about, what are some of the key optimization rules that they've defined?
So one of the key optimization rules is called group be joined to window. And this rule is used to transform queries that involve grouping and aggregating data and then joining the results back to the original table.
Right.
And so this is a very common pattern in SQL queries, and it can be very inefficient.
Yeah, because you're kind of reading the data twice, right?
You're reading the data twice, yeah.
And so the group be joined to window rule essentially rewrites the query to use a window function instead of a join.
Right.
And as we saw earlier, window functions can be much more efficient than joins.
Yeah.
Because they don't require the data to be read twice.
And this group be joined to window rule was actually applied in that TPC-DS Query 65 example.
Right.
Yeah, so that's kind of a concrete example of how this rule can be used.
Yeah.
And so I guess, another interesting rule is this join on keys rule. And maybe you can talk a little bit about that.
Yeah, so the join on keys rule is used to optimize queries that involve joining two or more tables on their key columns.
Okay.
And so key columns are essentially columns that are used to uniquely identify rows in a table.
Right.
And so when you join tables on their key columns, you're essentially guaranteed that each row in one table will match at most one row in the other table.
Right.
And so this can make the join operation much more efficient.
Right. And so the join on keys rule essentially tries to identify cases where queries are joining tables on their key columns, and then it rewrites the query to use a more efficient join algorithm.
Okay, so it's kind of taking advantage of that knowledge that you're joining on these keys.
Exactly.
And so you can use a more optimized algorithm.
That's right.
And I think, they also talk about how they use this join on keys rule to handle these things called scalar aggregates, which are basically just, subqueries that return a single value.
Yeah, that's right.
And so, if you have multiple scalar aggregates in your query, the join on keys rule can be used to merge them together.
Right.
So that you're only evaluating that subquery once.
Exactly.
And that was actually, I think they mentioned That was using query number 9 from the TPCDS benchmark.
That's right, yeah.
Yeah.
And they also have a rule called union Allen join. And this rule is used to optimize queries that involve using union all to combine the results of 2 or more subqueries that are joining different tables, but otherwise they're very similar.
Right.
And so the union all join rule essentially pushes the union all operation down in the query plan so that it happens after the joins.
Right.
And so this can make the query more efficient. Because it avoids having to evaluate the common parts of the subqueries multiple times.
Right. So you're essentially kind of rearranging the query.
That's right.
To do the common stuff once and then the union all kind of at the end.
Exactly.
Yeah.
And they also have a base rule for handling union all. Which is just called union all. And this rule is used to optimize queries that involve using union all to combine the results of 2 or more subqueries that are all operating on the same table. And so the union all rule essentially rewrites the query to evaluate the common sub-expression, and then it uses cross-joins and conditional logic to generate the different results for each branch of the union all.
Right.
So it's a very similar approach to the union all join rule, but it's just applied in a slightly different scenario. And they actually mention in the paper that these rules can often be applied in combination with each other to achieve even greater performance improvements.
Yeah, so it's kind of, it's not just one rule in isolation. It's often multiple rules working together to optimize the query.
Exactly. And they also talk about how they have to be careful about the order in which they apply the rules. Because applying one rule might create an opportunity for another rule to be applied. So it's a very complex optimization process.
Yeah, but I guess the good news for folks who are using Athena is that all this is happening automatically.
That's right.
You don't have to think about it.
You don't have to worry about it. It just works.
Yeah, you just write your query and Athena figures out the most efficient way to execute it.
That's right.
So I think, we've covered a lot of ground here. We've talked about, what are these optimizations? How do they work? What's the impact? But I think it might be useful just to kind of recap. What are the key takeaways for someone who's listening to this?
Sure. So I think the key takeaways are that Amazon Athena has implemented a number of sophisticated optimizations that leverage query fusion to significantly improve the performance and cost efficiency of queries with common sub-expressions. And these optimizations are applied automatically. So you don't have to do anything special to benefit from them.
And we saw in the TPCDS benchmark that these optimizations can lead to significant reductions in both query latency and data scan.
That's right.
Which translate to real cost savings for users.
Exactly.
And just to kind of highlight some of the specific examples that we talked about. We talked about how Group B join patterns are now being transformed into window functions. And we saw examples of that in queries like Q01, Q30, and Q65. And that this often involves something called decorrelation. Which is kind of a way of, simplifying the query. We also talked about how Athena is now smarter about handling multiple calculations that return a single value. These are the scalar aggregates. And we saw an example of that in queries like Q09, Q28, and Q88. And this involves using things like filter clauses and this mechanism called mark distinct, which is used for handling, distinct values. And then we also talk about how Athena now refactors branches of union all operations. And this was demonstrated in query Q23. And it involves recursively applying this union all on join rule. And then finally, we talked about how Athena is unifying relational aggregations in related subqueries. This was demonstrated in query Q95 and involves transforming semi-joins and applying the join on keys rule. So I think, this is it's really exciting to see how, the folks at AWS who are working on Athena are constantly pushing the boundaries of query optimization. And, they even say in the paper that, this is an ongoing area of development and that they're continuing to look for new opportunities to optimize queries.
That's right.
And so, I think it's really it's a testament to their commitment for making serverless data analytics more powerful and more efficient.
Exactly.
So for our listeners out there, I think the key takeaway is that, when you're writing your queries in Athena,
right,
you can be confident that the engine is doing a lot of work behind the scenes to make sure that your queries are running as efficiently as possible.
That's great.
And you don't have to be an expert in query optimization to benefit from these advancements.
Exactly.
So, I encourage you to think about the kinds of queries that you're running and whether you might be able to benefit from these optimizations.
Yeah.
And, just kind of keep an eye on the Athena documentation because they're constantly adding new features and new optimizations.
All right.
So, it's a really exciting time to be working with data in the cloud.
It is.
And Athena is a great example of that.
Yeah, it's a great service.
So that's all the time we have for this deep dive today.
Okay.
Thanks for joining us.
Thanks for having me.
And we'll see you next time.
See you next time.
Bye.